Welcome to this lesson on fitting functions to data in R. I think this is a really useful lesson. This is basically about how you go from having a bunch of data points to approximating those data points with some function that fits them pretty well. And R has some built-in commands that are given to you as part of the Mosaic package that are incredibly useful for doing this. And as always, one of the things you want to make sure is that over here in the Packages tab, that you have the Mosaic package activated here, that it's checked off. If it's not, you'll need to make sure that you click that checkbox here. All right, so let's start off with a little example. This is an example about natural gas usage. So we're going to get some data using the fetch data command. I'm going to say u equals fetch data of utilities.csv. And to remind you, fetch data is a command that we give you. It goes off to a special place on the internet that we have set up, and it grabs some data for you. And let's see what this data consists of. So you can come over here to your workspace tab, and if we click on U, we see a kind of spreadsheet looking thing, and we see there are different columns: month, day, year, temperature, KWH, CCF, and so on. And what we're going to be concerned with is temp and CCF, where T is the temperature on a particular month of a particular year, and CCF represents the cubic feet of natural gas that are used. And we want to ask about the relationship between those, and a good way to start is always just by plotting them. So we'll make a scatter plot. We use the plot points command. And let's look at natural gas usage in cubic feet, CCF, as a function of temp from the data set that we've called U. Okay, and if we do that, we get this graph appearing over here. And you can see it kind of has the shape you'd expect, at least very roughly. That is, if temperature goes up, natural gas usage goes down because natural gas is for heating, and you have to heat houses less if the temperature is higher. Okay, so now suppose that what we would like to do is fit a function to this data. We might have some function in mind, and we'd like to find the parameters for that function that best fit the data. So maybe the simplest function we could think of is a line that would go along here, something like this. Okay, so how do we find the line that best fits this data? There's a command, part of the Mosaic package called fitModel, that can do this. So we could type something like fitModel CCF as a function of, and now we give it a formula that's the formula that we have in mind. And if what we have in mind for our model is a linear function of temperature, I'm going to say something like A times temp plus B. And we have to, again, say what data set we're thinking of. Data equals U. And then once again, we have to capture the output of this procedure into something. So what running fitModel does is it returns a function that you can use that's the linear function that you're looking for. So let's decide to call that function f. We capture the output into f. We'll be able to use that function f. Okay, so now we might want to just take a peek inside of that function and see what values of a and b were found. We can type coef of f, 1f, coef of f, and we see that a, which is the slope of our line, was found to be about minus 3.46. The y-intercept is 253. Now, a very natural thing to want to do is to plot that linear function that we found on top of this data and see what it looks like. So you know how to do this. It's the plotFun command, and we would like to plot f of temp as a function of temp, where now temp is our independent variable, and we can give plotFun a range. So let's do temp lim. The limits of temperature are a range from 0 to 80. 80 over here on our graph. Okay. And what we're going to do is we can simply add this to the graph that we already have. So I'll say add equals true. And we get a line that looks something like that. Not a bad fit, right? You might wonder if you can do better than that. So let's fit a different model, okay? So we'll do fit model, and let's do, again, cubic feet of gas. And here we'll make up a different function. We're going to do A times temp plus B. That's a line again, but we'll add another component, C times the square root of temp. There's no reason you should know to guess this. I'm just giving you a possible function. And we have to tell it that the data set equals u. And as always, we have to capture the output of this into some function. Let me call it f2. Okay? And then we could go ahead and we might want to add that to our plot as well. So I will do plot fun f2 of temp as a function of temp, where temp.lim equals range from 0 to 80. I want to add that to the current graph. And maybe let's make sure that it's in a different color so we can easily distinguish it from the blue curve that's there now. Let's say col equals red. Okay, and we get this curve here, which, I mean, you might be tempted to say looks like a slightly better fit. It sort of captures a little bit of the curving of this data set. There are ways to be much more precise about how good the fit is. But for now, let's go on to a different example. So thus far, the example has been that the output variable depends on one input variable, but this this fit model command works just as well when you have an output variable that depends on more than one input. So we're going to look at some data for used cars. So I'm going to do fetch data, and the data set is used Hondas. .csv, and let's capture the output of that into a variable that we'll call Hondas. Okay, if I want to see what's in that data set, I'm going to close this little U here, and I'm going to click on Hondas. We can see price paid for a car, the year of the car, the mileage that was on the car, where it was bought, the color, and so on. And it seems reasonable to think that the price might depend on the mileage and on the age of the car, right? Like, if a car has a lot of mileage on it, you might want to pay less for it. If it's older, you might want to pay less for it. So we're going to try to make up a very simple model for this, and we're going to do fit model, price as a function of, and we're going to make up a simple function that's linear in age and mileage. So linear function can have a constant in it, and we'll do b times age plus c times mileage. So this is like a linear function of two variables. It's linear in mileage, it's linear in age, and there's a constant. And we have to tell it the data set, data equals Hondas, and then we have to capture the output of this, and I'm going to call it car price 1. Price 1 equals, okay? And if you're interested, you can, of course, look at the coefficients in there. Coef of car price 1. You see that A is a positive number, B and C are both negative numbers, and that makes sense, right? So that if the age of the car goes up, the price will go down. And if the mileage on the car at the time of sale is bigger, if that goes up, then the price will go down as well because the coefficient C is negative. That makes sense with our intuition. And we can, as always, plot the output of this. So we're going to plot fun of, and our car price 1 function, and we're going to do it as a function of age and miles, and the independent variables are age and miles. And then we can tell it some ranges, and we'll do age.lim equals a range from 2 to 8, and the miles range, miles.lim, is a range from 0 to 60,000. Okay, and let's see. That doesn't look quite right to me. And the reason is that I put a lowercase m in miles here, but I used an uppercase m here. So I look back at my previous command, there's my error. If I want to recover my old command, I can arrow up, and I can come over here, and I'm going to edit that to be a capital M. Ah, there's the plot I'm looking for. Okay, so we see car price as a function of age and miles in this nice contour plot here. We could make a more sophisticated model that includes some kind of interaction between age and miles. And so, let's see, I'm going to arrow up until I get to my old command for fit model. Here it is. And I'm going to make a new model, car price 2. And in this, price is going to be a function that's A plus B times age plus C times mileage plus D times their product. And that product is what represents an interaction between age and mileage. Like maybe at high mileage, the effective age is different than its effect at low mileage. So we can go ahead and run that command. If you're interested, you can look at the coefficients. They look something like this. And of course, we can go ahead once more and plot what this looks like. So I'll arrow up to get my old plot fun command. Now we would like to do car price 2 as a function of age and miles. And we can plot over the exact same ranges if we want. And it looks something like this. We have contours that are a little bit curved. And that has to do with the presence of this interaction term. It's not a linear function anymore. For the examples we've done so far, the parameters in the models, our A's, B's, and C's, and so on, have appeared in a linear manner. So even if the functions themselves have not been linear, and the last function was not a linear function, the parameters just appear in a easy linear way. It's not like the parameter itself is inside of a sine or a cosine function or inside of a logarithm or an exponential. And that makes the problem pretty easy for R to solve. If the parameters appear non-linearly, things get a little more complicated. So this next example is an example of non-linear parameter fitting. And to get started, let's load some data. So I'm going to say inc equals fetch data of housing, that's income dash housing.csv. And so what's being loaded is a data that's about, well, you can see what it's about if you click over here on this variable. There's income, maybe income levels or income brackets, the percentile that places that income in, something about crime and abandoned buildings, and so on. But the particular data we're interested in is going to be the percentage of households that have 2 vehicles as a function of income bracket. Okay, so we're going to plot points, and we'll plot 2 vehicles, which is one of the columns of this data set, as a function of income, where data equals this variable inc. Okay, and we see this graph appearing over here. Okay, at this point, you can see it's something that raises and then starts to level off. That makes sense. Households with smaller income, a smaller proportion of those should have 2 vehicles. The more income there is, maybe you expect the proportion of households having 2 vehicles to go up. And of course, it can't get past 100%, so eventually this has to level off. At this point, we have to sort of hypothesize a model that might fit this function. And so I'm going to say a few things about that. So here's the deal with the function that we're going to propose as a model. We're going to guess a function of the form a plus b e to the k times income. Okay? And the reason for this is that if you went back to the graph that was 2 vehicles as a function of income, it had data points that kind of went up like this and leveled off, okay? And if you look at this function, it has the ability to do that for appropriately chosen a, b, and k, right? Those are the 3 parameters, a, b, and k. So the first thing is that we expect that k has to be negative. If k is positive, then as income gets really big, the magnitude of e to the k times income grows exponentially, which isn't what we see in the graph here. So k is going to have to be a negative number. And with that in mind, as income gets really big, you get e to the minus something really big. That goes away. That's 0. So the idea is that for large income, the value of this should be approximately a. And we expect that for large income, it might approach 100% of households having 2 vehicles. So we're going to make a guess. And we're going to need these guesses. And our guess is going to be a equals 100. Now, if a equals 100, we can figure out what b is. Our guess for b is that if income is 0, 0% of the households will have 2 vehicles. Can't buy any cars if you have no money. If you imagine plugging in 0 for income, e to the 0 is 1. So you need that A plus B equals 0. And that means that B, we're going to guess, is near negative 100. We might be off for the best fit. We're just making a very simple guess. Okay, the next thing we have to guess is something about the constant K, right? This exponential constant. And one thing we can do is we could look back at our graph of points and try to use the half-life to estimate it. And so if at income equals 0, it's here at 0. And we could ask, when did it reach the midpoint of 50% of vehicles, right? That's halfway to 150. And if we want to know, we could always go back and take a look at our graph. If you go back and look at the graph, it looks like that point is somewhere around 25,000. It's a very rough estimate from the graph. And then we can remember the equation for half-life. And half-life says that the constant is equal to the natural log of 1/2 divided by the half-life. And we're going to guess that our half-life is 25,000. It takes going up to 25,000 to move halfway up this curve. So natural log of 1/2 over 25,000, that turns out to equal about minus 2.77 times 10 to the minus 5. Okay, so again, we're going to do this more exactly in R, but we're going to have some guesses. And our guesses are going to be A equals 100, B equals minus 100, and K is minus 2.77 times 10 to the minus 5. Let's go ahead and see how we use this. Suppose, for now, that we just try to fit our model. I say F equals fit model, and I'd like to predict 2 vehicles as a function of A plus B times the exponential function of K times income. The data comes from a variable called inc, and I tried to run this model, and I get an error. And basically that error means the procedure failed. And the reason it failed is that this parameter k appears inside an exponential function. That means it appears non-linearly, and R has a hard time. We got to give it some help. The help we're going to give it is our guesses. So I'm going to run this same command again, but I'm going to add something. I'm going to add start equals list of some stuff, and the stuff is our guesses. A equals 100, B equals minus 100, K equals the natural log of 0.5 divided by 25,000. That worked. If I look inside and ask what are the coefficients of F, we can see their values here. And they're not too far off from what we guessed, but they're more exact. And now we might like to go ahead and plot our fit function on top of these data points. And so we'll use the plot points command, or sorry, the plot fun command. And the function we'd like to plot is f of income. As a function of income, we could say income.lim equals range, let's do 0 to 100,000, and I would like to add it to the current graph. We get a very nice looking graph like this. All right, the next thing we might like to ask is how close are the data points to the curve that we have fit. Another way of saying that is that for any given horizontal coordinate of a data point, so think of taking a vertical slice like this, there's two things to compare. One is the y-coordinate of the actual data point, one is the y-coordinate of our fit model, of our predicted function. And the difference between those two things, the distance between those 2 points, is called the residual. And so we can look at those numerically. First, let's figure out how to get those two different sets of y-coordinates. If I want the y-coordinates of the data themselves, that's easy. That's just the 2 vehicles numbers. So I can type inc $2 vehicles. That means take the 2 vehicles column of the inc variable, and that just gives me that list of numbers. Now, if I wanted to get the values of our function at the corresponding x coordinates, what I have to do is take the values of income and plug them into our function. So to get the values of income, I do inc $income, but I want to take those values and plug them into our function f, right? So that's these values. If I want the difference between those two things, I just have to subtract. So I can do inc $2 vehicles, that's the actual values, minus f of $Inc. $income. Those are the values predicted by our model. And I'm going to save that in a variable called resids, which stands for residuals. Okay, and we can see what those are. There's some numbers here. Where it's positive, it means that the data point's above the curve. Where it's negative, it means that the data point is below the curve. Okay. We often will talk about the sum of the squared residuals as a measure of the goodness of fit of a model. And I won't go too much into this here, but it's just to say that if you want to add up these residuals, their squares, you can take them, square them, ask for the sum, and you get this number here. All right, I know this was kind of a long lesson, but thanks for watching the examples, and I think it'll be really useful for you. I hope you try to practice some problems involving fitting models to data points.